Hi guys, so for this week, I'm going to be going over linked lists. I'm going to do a quick recap of what you guys learned in lecture, and then I'm going to be going over a few questions on the CSM worksheet. So let's get started. For every linked list, there will be a value, and you can access that using, let's say, node.value, and that will return to you an integer that is stored within that node. There also is a .next, which will sort of bring you or point you in the direction of the next linked list object. And then there's also a sentinel. This one should be pretty foreign to you guys. I don't think you learned it in 61A, but it is the node at the very front of every linked list. We should keep in mind that this doesn't actually represent any useful information. For instance, the number that the sentinel stores does not tell you anything about your current list, nor is it an item in your list. It is just sort of a way to make things easier when you code things out. I'll get to that later. So a few things that you should note about the sentinel node is that it can never be null and it always points to the sentinel node. So sentinel is sort of an attribute that you can access, and you can think of it as a pointer that always points to the sentinel node. At no point in your code should you ever be changing that. You should not be reassigning the value of sentinel. And we also know that the first node of your linked list, if it does exist, will always be accessed by sentinel.next. Again, I just want to reiterate that sentinel is not actually the first item in your list. And we also know that for sentinels, because the value does not matter, we can assign any integer to it. And like every other node, you can access that integer assigned to it using .item. Essentially, we use sentinel nodes because some linked lists have a null as the first items and some don't. So to make things sort of simpler and like the same across everywhere, using a sentinel node eliminates the need to handle these special cases of having a null first. And that could be really helpful when you're sort of writing new code. So overall, it just makes things easier, and this is most clear when you're working with complicated programs. Okay, done. Okay, so now I'll be talking about singly linked lists versus, what the hell happened? Okay. So now I'll be going over the difference between singly linked lists versus doubly linked lists. So as for similarities, they both have a dot value, they both have a dot next, they both have a sentinel. The difference is, however, is that doubly linked list has a dot prev, which means that you can not only access the item in front of you, but you can also access the item behind you. And that's what dot prev does essentially. And there are two approaches that you can sort of take when you're constructing a doubly linked list. The first one is that you create two sentinels, which is at the back and the front, as opposed to the singly linked list that only has a sentinel at the front. So this one, you can sort of imagine your linked list as being sandwiched between the two sentinels. An alternative to this is to have one sentinel at the front, but have the linked list be circular. This takes quite a while to explain. So if you guys are still confused, definitely check out lectures 5 and 6. Josh Hugg explained it amazingly. So yeah, it's a sort of like visual representation of what each of them look like. You can see sort of a diagram over here. Okay, so now we'll be going over question 4 on the CSM worksheet, and I'll basically just read the question first. They're asking us to implement a function called center, which returns the middle node of the doubly linked list. If there are an even number of nodes in the list, return the one to the right. And you can assume this doubly linked list has one sentinel at the end and one at the beginning. So I've sort of drawn out a sort of messy diagram of the two different cases that you're going to be facing in this problem. It's sort of hinted at in the question, if there are an even number of nodes in the list, which you can sort of take as realizing there's going to be two cases, right? So there's going to be a doubly linked list with an odd number of nodes. So this one over here. Hold on, Yep, this one over here. And then there's going to be one of even length, like this one over here. So yeah, you're going to be thinking about how you could approach the problem in both cases and whether or not they even need to differ. So yeah, the first thing that you can sort of realize is when you're looking for the middle node of a doubly linked list, one way you can do that is to use 2 pointers. For instance, initializing one in the very front of the doubly linked list and initializing one at the very back of the doubly linked list. And you sort of, keep moving them closer and closer together up until they meet in the middle. You'll recognize soon after that this essentially only applies when you're working with odd length doubly linked lists, right? If you imagine it, they move one every time, then eventually they will end up at the same node only if the length is odd. Otherwise, they might actually end up pointing to nodes that are right next to each other. So that's one thing to consider when we're crafting the solution. So let's start off by doing what I said in the beginning, which is creating sort of initializing 2 pointers, right? You can imagine this over here, 2 pointers at the beginning and at the end of the list. So I'm going to be calling the pointer at the beginning of the list left, and I'll be calling this, yikes, my tablet will work. Okay, left and right. So let's just do that over here in code. I'm going to be giving them the names left and right. And we have a handy trick to access the front of a doubly linked list and to access the last element in a doubly linked list. Now we need to think about, what are we going to be doing in this while loop? Well, as I mentioned before, to find the middle, we essentially have to bring them, both pointers, closer and closer and closer to the middle, in every step. So I'm going to be doing that over here. So we know we're going to be reassigning the value of left, and the left pointer needs to be going right. So we're going to be calling left dot next. So, left dot next is this one over here. Therefore, you can imagine it as moving the pointer over there. So, in one step, we're moving the pointer over there because the previous node's dot next will be this node over here. And then we're going to be doing the opposite to right because we need it to move left, right? So going to be reassigning the pointer right, and it's now going to be pointing. Oh, I just realized capitalization. But yeah, we're going to be moving it left by 1. And as you can recall, for doubly linked lists, we can go both directions, right? We just have to use dot prev. So right equals right dot prev. All right, so we already have, the huge body of it done. We just need to figure out what are the conditions for the while loop. Well, you can see here that there's going to be 2. So let's try see if we can think of 1. So as we mentioned before, how would we know if we are in the center? We are in the center, or we found the middle node of a doubly linked list. For odd length doubly linked lists, it would be something like this, right? Both pointers would be pointing at the same node. And that means that you're in the middle of an odd number linked list, because you can sort of imagine it as they're all moving 1, 1, 1 until they meet in the middle, right? If you guys need to convince this a bit more in your head, try work through a few examples. So yeah, that could definitely be one of the conditions, right? So while left is not right. Right, that makes sense, because the moment that this while loop ends, we should already have our answers. We shouldn't be moving the pointers anymore. So once we know left and right are equal, we don't need to be incrementing the pointers anymore, right? So we need to exit the while loop. That makes sense for odd length linked lists. But how about even length linked lists, right? There, again, might be this case over here, where we know we hit the center when left and right are directly next to each other. So if you think about how you could represent that in code, you could essentially just do this. Left dot next not equals right. All right, so we're nearly done. We just need to be thinking about this condition over here. So if there are even number of nodes in the list, return the one to the right. Return the one to the right. So it essentially means that in this case, once we find out that we're at the middle, right, that the left pointer is right next to the right pointer, we're going to be wanting to return this node. And there's a very simple answer. You just return right. That's it. So now we'll be moving on to the second part of question 4, which is 4.2. It asks us to implement a function called fold over here, which should modify a doubly linked list by folding the first half of it over the second half of it and merging the intersecting nodes by summing their values. They also mentioned that we don't care about the sentinel nodes values in this case. So yeah, they give an example here, which is an even length doubly linked list. And they're basically asking us to implement or pass this into the function fold. So the way I like to think about this is sort of as a flip phone, where this is like one part of the flip phone, this is another part of the flip phone, and the hinge will be in the middle here. So you can sort of imagine it as a flip phone closing just like that. And as you can sort of imagine, the 3 will end up overlapping with the 7, and the 1 will end up overlapping with the 2. So how can we merge these overlapping nodes? As mentioned before, we just sum them up. So 1 plus 2 equals 3, 3 plus 4 equals 7. So as you can see here, the result is a doubly linked list with the values 3 and 7. Now we have an odd numbered doubly linked list. And in this case, we can sort of use the same idea. This is one part of the flip phone. This is one part of the flip phone. And the 2 in the middle is the hinge, right? Again, these are like sentinel nodes omitted. So when we sort of close the flip phone, we get that 1 intersects with 3. Add them up, we get 4. However, because 2 is part of the hinge, we're just going to include that in the final result. Therefore, the final values are going to be a doubly linked list with values 2 and 4. Okay, so we can start coding up the solution. Similar to the first problem, I'm going to be using a 2-pointer approach where I will first initialize an int node called left that points to the first item in the list, and then an int node called right that points to the last item of the list. And as you can notice here, they initialized a variable over here called an add counter. And it's essentially the size of the doubly linked lists divided by 2. And you might be thinking, right, like what could this possibly be? But you also need to recognize that we need to keep track of how many values we need to be merging or summing together. And that's actually what add counter is keeping track for us. It's nice to recall that due to Java and just the way integer division works in Java, size over 2 will always return an int value, not a float. For instance, if size were like 5 and it would be 5 over 2, it would actually just round it down to the value of 2. So that's important to keep in mind. Now we're going to be entering the while loop. So let's leave the while condition because we're still not sure what we're going to be doing in every iteration. But we do know one thing for sure, because this is a pointer problem. We want to be essentially adding opposite ends of the list every time, right? You can sort of think of it this way. Let me just write it out. Let this be an example, right? So if we initialized the left pointer over here and the right pointer over here, we want to be adding the values of wherever the left and right pointer are. Then we want to be moving them, right, in every iteration, and then add these values, right? And then we add these values. So yeah, we want to keep moving the left and the right pointer. So at that point, it becomes clear to us that in every iteration, we want to be reassigning the value of left to be left next. And we want to be assigning the value of right to be a right.prev. Okay, cool. So we got that part down. Now we need to think about, what else these empty blanks could be. Let's start thinking about the add counter. So in this case, in the case that there are like 4 elements in a doubly linked list, then add counter will be initialized at 2, right? Just 2 over here. And that essentially tells us how many pairs of values do we need to be adding. Of course, once we add, 3 and 8, the pairs left that we need to add to each other decreases. Specifically, it decreases by 1. Therefore, we need to decrement add counter by 1. Another way you could say this is minus equals 1. I mean the same thing. And then from here, you can kind of realize that we only want to be moving these left and right pointers, up until we run out of things to add, right? And again, we're keeping track of that using add counter. So we know that add counter plays a role in dictating how long our while loop goes. Therefore, it will be add counter greater than 0. Because once add counter hits 0, that means there are no more values to sum together. That means we're done, right? But there's one more blank missing. And it's actually the most important part of the question. It's actually adding the values to each other. So what we're going to be doing is I'm going to be changing the item that the left pointer is pointing to. And I'm going to be changing that to the sum of where the left pointer is pointing and where the right pointer is pointing. There you go. Okay, so we're essentially nearly done here. There's just some final considerations we need to take into account, namely reassigning the value of first. As you can see here in this example, the first node here was 3. Over here, the first node was 3. And now in the new doubly linked list, the first value will be actually 4. In this example as well, the first value was 3, and now it's going to be 11. So we need to think about a way that we can reassign the value of first. And there's actually some really important observations you could be making here. For instance, in this first example, 3, 4, and 7, we can tell that the first value is actually the middle of the list, right? It's for, odd length, doubly linked lists. It's very clear that the answer is the middle. And if you notice, that's actually completely in line with the function that we made before this, the function center. In fact, the value of first is actually the center of the original doubly linked list, right? So yeah, we're going to be reassigning the value of first. And we also want to make sure that there is still the sentinel node on the left of it. So, this wasn't explicitly part of the problem, but we can imagine that there are 2 sentinel nodes on either side. And we want to make sure that they're properly connected. So knowing that they're behind the first element, we can just assign first.prev's pointer to be sent front, which is the front sentinel node. And then we're going to do the opposite, which is, sent front dot next equals first. You can sort of think of it as something like this, right? Oh, sorry. Something like this, right? Where this is the sentinel node. We are setting first, let's say this is first.prev to point to the sentinel node, and then its next value should point to the front. All right, and one last thing we need to do is we need to set the size to be add counter. There you go. And you're done. I hope that was helpful.